one other technique that you can use when you are integrating some functions. We looked at one example yesterday. Today we continue with another example. The basic idea with the integration by parts is you need to, you'll have a product and you need to identify which one you are going to integrate and which one you are going to differentiate. And then you integrate the one you say you'll integrate, differentiate the one you say you'll differentiate, and then substitute them into the formula. In the formula that you get, you still have something to integrate like we have over here, except usually what you have to integrate the second time round is easier than what you started with. So another example. This one. The integral of x squared e to the power of 2x dx. So we have to integrate this. The first thing we said, pick your u, that is the one you're going to differentiate, and your dv, that is the one you are going to differentiate, because you have a product over here. Okay, so here we say u is equal to x squared, and then our dv is going to be e to the power of 2x dx. So I differentiate u, we get du is equal to 2x dx, and then v is the integral of e to the power of 2x, which is e to the power of 2x divided by 2, or just half e to the power of 2x. So now that I have these four terms, I substitute them into the formula. So the integral of this, or to write it, of x squared e to the power of 2x dx. This is u times v. So you multiply these two, so it's x squared times half e to the power of 2x, which is half x squared e to the power of 2x, and then minus the integral of v multiplied by du. So half x times, 2x times half e to the power of 2x, so minus x e to the power of 2x dx. Okay, so you can see I still have something to integrate over here. And looking at this one here, there isn't any other technique I can use to integrate it except integration by parts. So with this question, I have to integrate by parts twice in order to get to my final answer. So this one here, again, I must pick a u, I must pick dv, and then find du and v, and then substitute them, and then hopefully the next time the integral I have to do does not require me to use by parts. So our u here will be x, then our dv is e to the power of 2x dx. Then this means that du is equal to dx, and here v, the integral of e to the power of 2x with respect to x is just half e to the power of 2x. Okay, so I have my four terms. Now I can substitute this. So don't forget about the minus when you write uv and the integral of v du. Okay, so doing that, on the left hand side we have this term here, half x squared e to the power of 2x, that was there. So it's half x squared e to the power of 2x, and then minus The whole thing is minus because that is what the integral of this is. So it's negative u times v. So it's half x e to the power of 2x. And then again minus the integral of v, which is half e to the power of 2x multiplied by du, which is just dx. I have half e to the power of 2x dx, and then I can close my brackets. So this is a half x squared e to the power of 2x minus a half x e to the power of 2x, and then this negative and negative will give me positive, and then the half can go outside the integral, and then I integrate e to the power of 2x, that's half e to the power of 2x. The half from integrating this will multiply this half here, and then I have 1 over 4 e to the power of 2x. And now there's no integrals left, so I add my c over there. Okay, so you can see with this question, sometimes when you integrate by parts, the answer you get from that, you still have to integrate by parts. So it may not be just one more time that you have to integrate by parts. It can be several times that you have to still integrate by parts. Okay, and then let's do another example. This was number 2. Number 3, integral of x squared ln of x dx. So again, you have to choose what are you going to integrate and what are you going to differentiate. Now, what you pick is entirely up to you, but you always, I think, try and pick what you integrate first, then the other one, because differentiating is easier. So you always want to pick something that you can integrate easily. Okay, so here I have x squared and ln of x. So I'm going to differentiate ln of x because integrating ln of x, it will require you to integrate using by parts. So I don't want to do that. So I'm going to say u is ln of x and dv is x squared dx. Then we integrate, we differentiate u, so we have du is 1 over x dx, and v is the integral of x squared is x to the power of 3 over 3. Okay, so I have all my 4 terms. Then I can just substitute them into the formula for integration by parts. So the integral of x squared ln of x dx, this is equal to u times v. So I have x to the power of 3 over 3 multiplied by ln of x minus the integral of v times du. So I have x to the power of 3 over 3 multiplied by 1 over x dx. Okay, so here bases are the same. This is x to the power of -1. So in the numerator, I'll be left with x squared, and then the 1 over 3 can go outside. So you can see that integrating this, I don't require by parts. I can just use my table of integrals. So this is x to the power of 3 over 3 ln of x minus 1 over 3 the integral of x squared dx, which is x to the power of 3 over 3 ln of x minus x to the power of 3 over 9, and then you add your constant of integration. And as always, you can always very quickly differentiate this and see if you end up back at x squared ln of x. So the answer you get there might require you to do some algebra so that it looks exactly like what you started with, but if you've done it correctly, the derivative of this is that function you are integrating. The integral of e to the power of x sine x dx. Again, pick what you are going to integrate and what you are going to differentiate. Now here, e to the power of x and sine x, both of them are fairly easy to integrate and differentiate, so it doesn't really matter which one you pick. So I am going to choose to differentiate sine x and then integrate e to the power of x. Okay, so I will say u is equal to sine x and dv is equal to e to the power of x dx. Okay, so this means that du is cos x dx, and here v is just e to the power of x. Okay, so substituting them here, I get the integral of e to the power of x sine x dx is uv e to the power of x sine x minus the integral of e to the power of x cos x dx. Okay, so we look at what we have over here, and again, I need to use by parts to integrate this. Okay, so sticking to how we pick them, we say u is equal to cos x and dv is equal to e to the power of x dx. So this means that du is minus sine x dx, and v is just e to the power of x. Now I substitute, so remember the minus, it'll be minus uv plus the integral of v du. So if I just look at the right-hand side for space, I have e to the power of x sine x minus u times v e to the power of x cos x, and then minus the integral of v e to the power of x du, and then minus sine x dx, like that. Okay, so this is e to the power of x sine x minus e to the power of x cos x. And now here I have negative, negative, negative. So that will be negative integral of e to the power of x sine x dx. Okay, so looking at this, it seems like our integral will never end because this is e sine x, and then next I can see the pattern that after this, if I use by parts again, I will have e to the power of x cos x and then e to the power of x sine x. So when we have something like this, what you do is you look on the left-hand side. So this is what we have on the left-hand side. And this term here is exactly the same as what we have on the left-hand side. So what we do is this term here, we take it to the other side, and what we will have is 2 times the integral of e to the power of x sine x dx is equal to e to the power of x sine x minus e to the power of x cos x. So now on the left-hand side, on the right-hand side rather, there is no integral. But here on the left-hand side, we have 2 times the integral. We're not looking for 2 times the integral. We're just looking for the integral. So what we do is we divide by 2, and that means the integral of e to the power of x sine x dx. This is a half e to the power of x sine x minus a half e to the power of x cos x, and now you add your constant of integration. Okay, so you will get integrals like this, which seemingly go in a loop. It's like they will never end. And with those ones, you should get to a point where what you have here, the negative of that, is the same as what you have on the right-hand side. So you collect those integrals on one side and then divide by whatever coefficient you have there. Okay, so there are some integrals like this. Usually they involve these e to the power of x and sine x because their integrals never end. Unlike x to the power of something, eventually you'll get x to the power of 0 and there's no x anymore. But e to the power of x, you can keep integrating however many times it'll never disappear. Okay, so that's that one. Okay, then we have the integral of ln of x dx. So like I said, this one here, you need to use integration by parts in order to work it out. So even though it looks like a single term, you can look at it as a product. You have 1 multiplied by ln of x. So it is a product, and you can use integration by parts. So you need to pick what you will integrate and what you will differentiate. So here I'm going to pick u is equal to ln of x, because if I say I'm integrating ln of x, it's exactly what I have in the question. So I won't be able to proceed. The only way is to say u is equal to ln of x, and that means that dv is equal to dx. And then we work out du. Du is equal to 1 over x dx, and v is equal to x. Then simply substituting, we have the integral of ln of x dx is u times v, so that's x ln of x minus the integral of v multiplied by du, like that. So this is just x ln of x minus the integral of dx, which is x ln of x minus x plus your constant of integration. So that one is fairly simple, nothing complicated there. And one more. Integral of tan inverse of x dx. Okay, so again here we have to pick u is equal to tan inverse of x, and dv is just dx, because if we swap them, then trying to integrate tan inverse of u is exactly what is given there, and we need to use by parts to solve it anyway. So the derivative of tan inverse of u, this is 1 over 1 plus x squared dx, and v is equal to x. Okay, so we have our 4 terms here. Now we can just substitute them to work out the integral of tan inverse of x. So the integral of tan inverse of x dx, this is u times v, that's x times tan inverse of x. And then we subtract the integral of v, which is x times du. That's x over 1 plus x squared dx. Okay, so we know how to integrate this. We've been doing integrals like this. We said here, this is not an arc-trig integration, because the numerator can be written as the derivative of the denominator. We just need a 2 there. So if we put a 2 there, we need a half outside. So this is x tan inverse of x minus a half, the integral of 2x over 1 plus x squared dx, which is x tan inverse of x minus a half. And here, this is ln of 1 plus x squared. And then you add your constant of integration. So that about covers all the different types of questions that you can solve using integration by parts. Now I want to show you a shorter method, shorter-ish, I guess, of integration by parts, which comes in handy when you want to integrate functions that involve you using integration by parts several times. So we look at this one here. Which question was that? This one here. Was it this one? No, not this one. Number 2. Yeah, number 2, I had to use integration by parts twice. Even the one with e to the power of x sine x, but that one, just 2 steps, you'll be done. But here, imagine if this was to the power of 6. So you can see what is happening. The first time I use integration by parts, the power of x reduces by 1. Then the next time, the power of x reduces by 1 again, and it continues in that manner. So if I had, for example, 6 here, the first time I integrate under the integral here, I would have x to the power 5 used by parts again. Then I have x to the power 4, then by parts again, 3, 2, 1, 0, and so on. That will take a long time if I am writing it like this. So we want a shorter way of writing it, but still using integration by parts. Let's look at, where's that example? Okay, so this is one that we did already. We want to find the integral of, let's say, x squared e to the power of 2x dx. Okay, so we are still using integration by parts. We're just writing it in a way that it is much shorter for us to integrate. So what you do is you put a d and you put an I over there. So D stands for whatever it is you're going to differentiate. I stands for whatever it is you are going to integrate. So you still pick your terms like that. So when we differentiate, when we worked this one out, we said that we will differentiate x squared and we will integrate e to the power of x. So what you do is you can differentiate the first time, you get 2x here, and then when you integrate, you get half e to the power of 2x. Okay, and I can stop here, but you can always continue as many times as you want. And then on this side here, you put the first column has a plus, then minus, then you'll have plus, minus, and so on. So you can see that if I stop here, and how we use integration by parts is you multiply these two, and then you get x squared, or half e to the power of 2x, and the sign here counts, so it's positive x squared times half 2x. That's the first part, you get it like that. And then this last column, last row rather, you multiply them and integrate. So you'll say minus the integral of x e to the power of x. So this is exactly what we got, dx. This is exactly what we got the first time we integrated it, and then we had to use integration by parts over here. So this time we just want to continue with our table. Let's add another column. We differentiate 2x, we get 2. We integrate half e to the power of 2x, we get 1 over 4 e to the power of 2x. And then here, our column of signs, we have plus, minus. The next one should be plus. So if I wanted to stop here, I would multiply diagonally. So it's this times that, then this times that, and then horizontally is what I will put in the integrals. So if I wanted to stop there, I would have x squared, sorry, it's half x squared e to the power of 2x, and then minus, remember the sign here counts when you're multiplying, so it's minus 2x, so it's 2 times a quarter, which is a half, so it's minus a half e to the x e to the power of 2x, and then I would say plus the integral, so it's this plus over here. Now I'm integrating horizontally, so I'd say 2 times half, which is half e to the power of 2x dx. And I think when we did it, we got to something like this, and here we could just integrate this without integration by parts. Okay, so whatever step you stop at, you will get to that point when you're doing it the long way. This is much shorter. So let's see what happens if we add another row in our shorter method. So the next one here is minus because the signs are just alternating plus, minus, plus, minus. When you integrate, when you differentiate 2, you get 0. And then when you integrate 1 over 4 e to the power of x, e to the power of 2x, you get 1 over 16. No, 1 over 8, because you divide by 2. So it's 1 over 8 e to the power of 2x. So if I wanted to stop here, I would multiply diagonally, and then these ones. And then what goes under the integral is 0 times this. And if we're integrating 0, we get a constant. So that will be the end of our integral. So now if we rewrite this, let me just make it smaller. Okay, so now if I write the answer after I've done it like this, we get x squared. So it's positive because that's a positive. Keep writing x squared. So it's positive 1/2 x squared e to the power of 2x. Then the next one is negative 2x times 1/2, which is just negative x e to the power of 2x. And then the next one is positive 2 times 1/4, which is 1/2. Where am I? I'm here, the third one. So it's 2 times 1 over 8. Yeah?
The second term is supposed to have a half.
Oh, yes. 2, it's half. Sorry. So it's 2 times 1 over 4. It's 1/2. So this is 1/2 x e to the power of 2x. And then the next one is plus 2 times 1 over 8. That's 1/4. 1 over 4 e to the power of 2x. And then we would integrate 0, and that is just a constant. Okay, and you can see even if you continued with your table, the derivative of 0 is just 0, 0, 0. So integrating horizontally would just give you a constant. And this is exactly what we got when we integrated it using the long way. Okay, so I find this helpful. For example, if this term over here, x to the power of 5, rewriting u dv du v every time can take you quite a long time, unlike if you have a table like this and you just integrate. So that's just the shorter method, which you can use if you want to. Okay, so let's look at some of the questions in exercise 4.2. Start with number 2. What's number 2 say? In 2, we have to integrate x squared cos nx dx. So n over here is a constant. Okay, so again here, we can practice using our short method, but writing u, du, dv, and so on is perfectly fine. So we need 2 terms, what we will differentiate, what we will integrate. So usually we differentiate x squared because the derivative will eventually go to 0. So we have x squared, and we will integrate cos nx. The first one is positive, and you can see that even if I stopped here, see there's no diagonal to multiply, but horizontally is what I will integrate. So I say cos x squared times cos nx, which is exactly what I have here. So your horizontal, your row is always what you integrate, and whatever point you're at, if you integrate this, you're back at the original question. Okay, but obviously we don't want to stop there. Differentiate 2x, x squared, we get 2x. And then we integrate cos nx. The integral of cos nx is sine, yeah, it's positive. It's sine nx, and then we divide by n. So this is sine nx divided by n. Okay, and then this is negative. Then I can differentiate again. I get 2. This is a positive row. And then if I integrate this, the derivative of sine nx is negative cos nx. And then I divide by n again. So in the denominator, I have n squared. And then I can differentiate again. I get 0. And here the integral is the integral of negative sine x, negative cos x is negative sine x. And then we divide by n again, we get n to the power of 3. So with this method, when I get to a 0, I know that I need to stop. Okay, because the derivatives after that are just going to be equal to 0. Then we said our answers or the solutions, part of the solutions are these diagonals, this times that, this times that, this times that, and then wherever we stop, the last row is what we integrate. But if I integrate 0 times that, it's just my constant of integration. So my integral of x squared cos nx dx. This is equal to x squared sine nx over n. Then the next term is negative, so it's negative 2x times negative. So negative and negative, this gives me a positive. So I have positive 2x cos nx over n squared. Then the next term, positive times negative, is negative. So I have negative 2 sine nx over n to the power of 3. And then the last term would be the integral of that, which is just my constant of integration. And then I am done. Okay, x squared over n, sine that 2x over n squared cos, and then 2. Okay, that's fine. Right, then next question, number 3. The integral of x to the power of 3 sine 2x dx. So again, instead of me writing my du, dv, u, and v, I'm just going to use the shorter method because I can see with this x to the power of 3, I will have to do integration by parts at least 3 times. Okay, so I have d, I have I. You pick what you want to integrate and what you want to differentiate. So here, usually we pick this one because the derivative eventually goes to 0. That's x to the power of 3, and then sine 2x is what we will integrate. So differentiate, we get 3x squared. Integrate, we have minus cos 2x over 2, or just minus a half cos 2x. Differentiate again, so this is plus minus, then plus, this is 6x. Then the integral of minus a half cos 2x is minus 1 over 4 sine. And then the derivative of 6x is 6, and the integral of minus a quarter sine 2x is positive 1 over 8 cos 2x, and then the derivative of 6 is 0. This last row is positive. And then the integral of 1 over 8 cos 2x is 1 over 16 sine 2x. Okay, and with your integrals, you can check, differentiate this, you should get this one, differentiate this, you should get that one, differentiate this one, you should get that one, and so on. So we've gotten to the 0, that tells us we need to stop, and then our answer is just these terms like that. And then the last integral is the product on our last row. So the integral of x to the power of 3 sine 2x dx. This is negative a half x cubed cos 2x. Then we have negative and negative, that will give us positive. So we have plus 3 times 1 over 4, this is 3 over 4 x squared sine 2x. Then the next one is also positive, so I have positive 6 times 1 over 8, 6, that's 3 over 4. X cos 2x, and then the last one, negative 6 times 1 over 16, that's 3 over 8, it's negative 3 over 8 sine 2x, and then the integral of 0 is our constant of integration. Number 6. Integral of x squared, hyperbolic cos of 2x. This one is almost the same as the one we just did now. Again, what you differentiate, what you integrate, first row is positive. So x squared cos hyperbolic of 2x. Then 2x here, and the integral is just sine 2x divided by 2, which is a half, then 2, and 1 over 4 hyperbolic cos of 2x, and then 0, 1 over 8 hyperbolic sine of 2x. So our solutions there, and then we integrate the last row. So the integral of x squared hyperbolic cos of 2x dx. This is equal to a half x squared hyperbolic sine of 2x, then minus 2x. We have 2 times 1 over 4, which is a half. So it's minus a half x hyperbolic cos of 2x. Then 2 times 1 over 8 is a quarter hyperbolic sine of x. And then we integrate 0 times that, which is just our constant of integration. Number 10. The integral of, well, this is a definite integral. We have x e to the power of minus ax dx. So with this one here, I can use the DI method, but I see that as soon as I integrate this once, I won't have to do a lot of integration afterwards. So with questions like this, I can just use, I won't have to use integration by parts again. You can use that method, it's fine, you'll get to the same answer. But with this one, I can just pick my u, or for us to practice doing it, say u is equal to x, dv is e to the power of minus x dx. This means that du is equal to dx, and v is minus 1 over a e to the power of minus x minus ax. Okay, and then we would substitute the integral from 0 to 1 of x e to the power of minus ax dx. This is u times v. So remember, this is a definite integral, or maybe what we can do is first ignore the limits, get our integral, and then work out the definite integral at the end. So this is minus x over a e to the power of minus ax, that's u times v, then minus the integral of v times du, which is x. So this negative and that negative will make it positive. So I have 1 over a e to the power of minus ax dx. Okay, so this is minus x over a e to the power of minus x, and then here the integral of this is negative 1 over a squared e to the power of minus ax. Okay, so I would add my constant of integration, then go back to the question and say that the integral, see, from 0 to 1 of x e to the power of minus ax dx. This is equal to minus x over a e to the power of minus ax minus 1 over a squared e to the power of minus ax, and then we integrate from 0 to 1. So here you just substitute the way you always do, from 0 to 1. Okay, so we substitute 1, we have minus e to the power of minus a over a minus 1 over a squared. I shouldn't put 1 in the numerator. And then I have e to the power of minus a. And that's my first term. And then minus, when I substitute 0, this is just going to be 0 because it's 0 times something. And then e to the power of 0 is 1. So this is minus 1 over a squared, like that. Okay, so working this out, just because I don't have space, the answer is this. This negative and negative becomes positive. So that is our solution there. We don't need the brackets at the end. Okay, so even if it's a definite integral, we still can use by parts, just that at the end we have to substitute the limits. Number 11, we have the square root of x, ln of x, dx. So here again, u is equal to ln of x, dv is the square root of x dx. So du is 1 over x dx, and v is 2 over 3 x to the power of 3 over 2. Okay, then this means that the integral of the square root of x times ln of x dx, this is u times v, so it's 2 over 3 x to the power of 3 over 2 ln of x minus the integral of v du. So we have 2 over 3 1 over x times x to the power of 3 over 2, and there's a dx over there. Okay, so this, let me simplify that. This is 2 over 3 x to the power of 3 over 2 ln of x. The 2 over 3 can go outside. Then inside we have x to the power of a half. Dx, which is 2 over 3 x to the power of 3 over 2 ln of x minus 2 over 3. Here multiply 2 over 3, then x to the power of 3 over 2 plus c, which is 2 over 3 x 3 over 2 ln of x minus 4 over 9 x to the power of 3 over 2. And then you add your constant of integration. Number 14, e to the power of minus x cos x dx. So let's try this one using the short method. So we said we need something to differentiate, something to integrate. Doesn't matter which one you pick here, because they're both equally easy to integrate and differentiate. So we have e to the power of minus x as what we're going to differentiate, and then cos x what we are going to integrate. So this is plus, the next one is minus the derivative. This is minus e to the power of minus x. The integral of cos x is sine x. And then let's do it one more time. So you can stop here. This product on the diagonal is a solution, and then you have to integrate this product, but again you would have to use by parts. So we can continue again, and the derivative is e to the power of minus x, and the integral of sine x is minus cos x. Now you can see with this one over here, it will never end, because this sine x cos x, the integral will never go to 0, and here the derivative will never go to 0. So when you multiply in horizontally, you will never get a 0. So how do you know when to stop? You stop when the product on the last row is what you have here. So a scalar multiple of what you have here. So you can see here I have e to the power of x cos x. Here I have e to the power of x and cos x. So that is where I stop. So I integrate e to the power of minus x cos x dx. This is these are my solutions, and then the final one is the integral along the last row. So the first one is positive, so it's positive times negative. My answer will be negative e to the power of minus, sorry, what am I doing? I'm looking at the wrong one. Okay, so this is positive and positive, so it'll be positive e to the power of minus x sine x. And then the next one, I have negative, negative, negative. That will give me negative e to the power of minus x cos x. And then the last one is positive and negative. This gives me negative the integral of e to the power of minus x cos x dx. But then you can see that this integral here is the same as what you have on the other side. So you can take it to the other side, and then you get 2 the integral of e to the power of minus x cos x dx, which is e to the power of minus x sine x minus e to the power of minus x cos x. And then you divide everything by 2 and add your constant of integration. So the integral of e to the power of minus x cos x dx, this is a half e to the power of minus x sine x minus a half e to the power of minus x cos x plus your constant of integration. Okay, so similar to the way we did one of the examples, except we wrote du, dv, and so on at each step. But with this method, you can still use it. You just need to know where it stops, because these integrals, these derivatives, they never go to 0. So there are more questions in the exercise. Make sure you practice them. Don't wait until the week of the test to try and practice everything. You won't remember anything in time for the test. So the way to do it is start practicing. I think this next test is going to be on integrals, and this is a very long chapter. Okay, so start practicing as soon as possible. Okay, so we'll stop here for today and continue tomorrow. Tomorrow will still be online. I haven't gotten any feedback from people I was waiting for, so we'll just be online tomorrow as well.